Hello, everyone. Welcome to today's webcast on how you can avoid design issues and reduce costs with SOLIDWORKS Plastics. I'm the moderator, Krista Prokos, and before we get started, I want to let you know that you can submit questions for today's presenter by typing them into the Q&A panel at any time. We'll collect them and address them at the end of the presentation. Now I'd like to introduce today's presenter. We're happy to have with us Nathan Sneller. Nathan is an application engineer at Fisher Unitech who has had a lot of experience using SOLIDWORKS simulation tools, but he believes anybody can use them, whether you have experience or not. Nathan, take it away.
Thanks, Krista. Hold on a second. That's the way it goes, isn't it? There we go. It's probably going to jump ahead about 20 slides now. Well, like Krista said, I'm Nathan. I'm fairly new to Fisher Unitech. This is my first webinar. I do hope you enjoy it. I've been using SOLIDWORKS since about 2004, and I've been teaching it at Grand Rapids Community College since 2009. And I've had the opportunity there, or really more the pleasure of teaching lots of students and seeing them go on to some pretty interesting careers involving SOLIDWORKS and 3D modeling. I spent the last 10 years running an engineering firm that specialized in electromechanical devices and also general contact engineering. So I've had quite a bit of experience in mechanical engineering and with electrical too. And I still do some of my own product development, and I'm in the trenches with you guys now and again. My role here is that of the ambassador of simulation, which means I'm here for all the SOLIDWORKS users. And I'm helping companies wherever I can, whether or not simulation software is involved. It's my job to do what I can to help you make your company more profitable. I believe that a happy, profitable person makes the best customer, so use me and abuse me. On that note, my email is always open. If you have a project you'd like a second set of eyes on, send me a few files or screen captures, and I'll talk you through your design, or talk through your design with you. We have thousands of customers, so if you're having problems finding a manufacturer or with a current manufacturer, I'm sure we have somebody in our Rolodex who's doing what you need already. We'll be glad to put you in touch. Apparently, I'm going to have to click the button that moves slides ahead and just not hit the space bar. There we go. Well, today I'm going to tell you about a product I developed using SOLIDWORKS. Now, I consider myself a pretty knowledgeable designer and engineer. I know most of the rules for plastics design. Uniform wall thickness, don't make your ribs more than 75% of your wall thickness, use big fillets where you can, gradually transition from areas of one thickness to another, etc., etc. I didn't really need to do a plastic simulation, right? These parts look pretty good, everything fits up. Well, I went through at least 3 mold changes before I got this far. It probably took me an additional 6 weeks of mold build time after samples went back and forth between me and my mold builder. Now, if I had SOLIDWORKS Plastics, I would have saved myself a lot of time and money, not to mention late nights, ornery emails, general anxiety, all sorts of things. Looking back, I wish I'd had SOLIDWORKS Plastics and bought it a while ago. So I like to make parts that are highly functional. Every feature I do has a specific reason for it. And I take a little bit of pride in each one of them because I think I'm smart when I come up with them. For example, here's a little structural support. The cost of the plastic is almost nothing, and I doubt the cost of my mold would have changed whether it was there or not. But it's there for a purpose. I was worried that somebody was going to push too hard on the button, which is circled on the right there. And without something to support that button, the board had to take all of the force and was liable to crack. Now, I may have had that similar situation happen some years ago, and we ended up replacing every single circuit board because the enclosure didn't support it well enough, and I think it cost about $80,000. So it was an expensive lesson to learn. Now, you're probably thinking, hey, Nate, that's a structural problem? Well, this is supposed to be a plastic seminar. What are you doing? Well, don't worry, it is. That little stand is a solution to a structural problem. It does a great job of preventing that printed circuit board from bending, but if that feature doesn't fully fill or isn't there when it's manufactured, it's a big issue. Now, I don't see these parts before they're fully assembled. The parts drop shipped to the circuit board manufacturer who assembles it all together, ships it to me for final testing. And if that feature isn't there, I'm never going to know about it. So I need to be fairly certain, if not 100% positive, that if my part fills, that feature is going to be in place. Now the agenda for the day today is to talk about the plastic part we looked at, what the features are, why they're important, which we touched on a little bit. Then we'll look at varying gate location, seeing what kind of effects or where we're prone for sink, air traps, and where the weld lines will fall. Once we've done that, we'll move on to checking whether we have a sufficiently capable machine or designing to a machine we already have, and then run our balancing. In the end, we'll have a chance for questions and answers. So first of all, let's take a look at the parts themselves. At the highest level, these two parts just function as an electrical enclosure. They keep the circuit board protected from fingers, popcorn, pop, trash, rodents, whatever the case may be. And when it's fully assembled, the circuit board really has no interaction with the outside environment. Now these are the 24 features I've identified that are critical to doing that simple thing of keeping the circuit board isolated from the outside environment. Each one of those need to be there, and if they're not, I don't have a good part. So you might be asking, well, what is SOLIDWORKS Plastics exactly? And SOLIDWORKS Plastics is a simulation tool that simulates how melted plastic flows within the mold during the injection molding process. The ability to simulate how that plastic flows in the mold allows us as designers to predict manufacturing-related defects, and we can change the mold geometry, the processing conditions, or the plastic material used to minimize those defects, saving energy, plastic, time, money, headache, all sorts of things. Here are two parts with different gating locations. The first, the one that's all colored here, is gated on the side near the parting line. And it's kind of interesting to watch the plastic flow. You can see what feature fills last. Now, if I were building a fixture and I wanted to detect if there was a short shot, I could kick off that fixture before my parts were done and put a little sensor in this corner. I don't know if you can see my mouse pointer or not. Yeah, shoot. In that corner there to see if the part had filled or if it hadn't. Now over here, if I were molding this in a single shot tool, I'd probably inject it right in the middle, which has some advantages in that the part is sort of internally balanced. It's not, one corner isn't seconds apart or a long time away from the other one and what gets filled. So just a couple of different options. Now flipping over here to air traps and weld lines. On the right-hand side, it's a little hard to see, but all these purple dots show where the air is getting trapped. In order to force plastic into a mold, you have to force the air out. And we do that through a process called venting, and it's certainly easiest to vent along the edges or where the two parts come together. And through a little bit of prior knowledge and a little bit of luck, all the air gets trapped near the parting lines in this part. So it's fairly simple to add a gate in, let the air out, but we know it ahead of time now. I'd be very concerned if I had an air trap right in the middle of the part and there might be a hole and I didn't have a good way to vent it. On the left, you can see where the weld lines form and at what temperature. Now, the weld line that concerns me the most is the one near this little button feature. Again, I'm not sure if you can see my pointer, but it's the top left corner. It goes from a square window to a kind of horseshoe-shaped one. That's a thin region and it might be weak, and I probably don't want, especially since I have people pushing right there, an area where it's prone to breaking. So by moving the injection location, you can see it's down the bottom just slightly to the left. There's a little magenta triangle. If I move that up to the top on the right, I get a better simulation. Now I've created a new problem here where my weld line is across my hinge, but it's certainly not as troublesome because if that cracks right there, I've still got 95% of my button. I would probably move my gate location a little bit to try to push that weld line out of my hinge, but I'm getting very close there. In these plots, we take a look at sink. You've got the top and the bottom faces of this. Everything is fairly uniform. It's prudent to take a look at the graph on the left, the bar, just to see how much variation we have in sink from, looks like 11 thousandths to 17 thousandths isn't a terrible amount. So I did fairly well there in my design. But moving on to the second half of the mold, next we look at cooling time. Here you can see the parts that take a little longer to cool. Again, it's not a terrible problem here. It looks like the difference between about 4 and 5 seconds for the most part. If this becomes the bottleneck, I would go in and adjust the design or cooling channels in order to reduce that time. But now moving on to the next part, you can see here I didn't pay close enough attention. I've got a cooling time. Most of the part is cooled within about 3 seconds, but I have some areas that are taking 10. So an extra 7 seconds of cooling time. Had I done a plastic study on this, I would have noticed how big of a problem it was. When I made it, I knew I had a slightly thicker region there, and I didn't really give too much thought to it. I just knew, oh, it's going to be thicker, it's going to take a little longer to cool. But if that's hurting my cycle time by at least 4 seconds over the other part and 7 seconds over this one, depending on the quantity I'm running, that could be a significant cost savings. If my machine time is half my part price, could be a quarter of the cost of my parts. So in hindsight, I should have rotated those 90 degrees so they were on the same side as the slides in the tool, and then I could have cored that area out. Oops. Now, once we've got that stuff figured out, it's time to look at the molding machine that we're going to use. I had a 50-ton Van Dorn injection molding machine at the time. So if I were going to run this in a single tool, I would have ran it in that. And you can see, just looking across the graph, that the clamping force at the very end tends to be about 32 or 33 tons. And if it's a 50-ton machine, I'm well within the parameters of the machine. If this exceeded my 50 tons or were right on the edge, I'd run into the possibility of flashing the mold, which means to force out little bits of plastic around the parting line because the machine isn't strong enough to keep it closed while it's injecting plastic, and that's never good. The solution is to put it in a bigger machine or generally have somebody with a razor blade trim that flash off. Now the other side of that is you can have too much clamping force too. Now this is generally set on the machine. You can say, hey, don't clamp at 100 tons when we only need 33, or at 50 when we only need 33, maybe do 40. But I found an interesting article when doing research for this. It was on Plastics Technology Online, where the author went into the problems associated with too much clamping force. On the left, you can see a mold split in half, which had to be an expensive problem. Hopefully it wasn't a huge volume part, because I can't imagine how long it would take to replace that, probably 2 to 3 weeks, up to 2 months. And on the right-hand side, the molding machine actually split. Now, I know what I would have done if that were my machine and I saw it on March 5 of 2015. Would you have done the same thing? If you said, I would have drilled a hole right about where that red line is to put in a stress relief so that crack doesn't propagate all the way down, you and I would be thinking the same way. Think of that as just blunting the edge of the axe. But I digress. But the moral of the story is, more isn't always better. Linus sometimes is just more. Anybody know what line that movie's from? It's Sabrina. So the next step is looking at the injection pressure. My machine had an max injection pressure of 23,000 psi. This part requires 11,600, so we're definitely within the capabilities of that machine. Now finally, we're going to take a look at family tools and runner balancing. So being a perpetual cheapskate, I don't like to pay for tool mold bases or machine time in 2 machines when I can get away with 1. My volumes aren't large enough generally to justify multi-cavity tools for the same parts, so most of my parts end up in a family tool. I know every region and industry has its own jargon, so help me define a family tool. In case our lingos don't line up, a family tool is a mold that has multiple cavities for molding parts, but the cavities are different shapes. For example, the lid and the housing itself in this part, or in these parts. So in my first attempt, I just threw a very crude runner system in. Just ran the sprue right down to the runner and then went to both parts. On the right of my screen, you can see that at 0.625 seconds, my lid is completely filled, but my enclosure still has a ways to go. That filled completely at 0.77 seconds, so that's an 80%. The lid is filled at 80% of the total fill time, or 20% difference. Not real good. The next thing I did was I tried to make a little more room for it to play with, and I ran a runner balancing equation. Now I only iterated it 10 times, or feature rather, program. I only iterated 10 times instead of 20 or 30, which would have gotten me closer. But here I'm closer to 90% of my cycle time when the second part is filled. I could probably get that down to 99, or get that up to 98 or 99 with a few more iterations. But it's getting dialed in, and that's the point. Now, the family tool, or the runner balancing for tools, is really neat. It's so useful, there really isn't a whole lot to show. All I had to do is run the first flow study with equal size runners. Then I opened the runner balancing, which you see on the left there, and set the max and min and the number of iterations and let it run overnight. Come back and the parts are very close to being perfect if you let it run more than I did. So the mold engineer at a company I worked for long ago told me they used to use set screws in the runners to balance all the parts. We'd have 24 cavity tools, and they didn't run plastic simulation on it. So they would shoot it in partial shot or short shots to see which one filled when, how long it took. And then they would adjust the depth of the set screw in each runner to speed up or slow down how that filled, which worked great for about a day or two, because as the mold expanded when it was heated and cooled when it was cooled, or contracted when it was cooled, the set screws would move positions, they would come out, they would generally have to be rebalanced every couple of days. It was an absolute nightmare. Having a balanced system where you know it's going to fill the way you want it to every time saves countless bad parts, headaches, downtime, machine time, maintenance time, all sorts of things. Anyway, that was, if I have a part that's the way I want it to be run, that was set screws. So to recap here, let's take a look at all the things I did wrong. I didn't specify gate locations, and my toolmaker had to make multiple guesses. I didn't go into great detail on that, but I know they tried at least 3 times to gate it before they settled where they did, which added close to 6 weeks to my product launch time. I didn't balance the runners ahead of time, and my parts to this day aren't filling quite properly. One fills before the other. And I have 2 large areas prone to sink, which are prolonging my cooling time, and it's hard to show it in the picture because the parts are black, but you can see visible shrink marks on my part in those areas, which doesn't exactly make me happy, but I have to live with it now. So if you or I are designing injection molded parts, SOLIDWORKS Plastics is almost essential. The cost of the bad parts or bad molds, it's really unquantifiable, at least for me. I think of it as an essential tool. So at Fisher Unitech, we can help you ensure that your plastic parts are designed for manufacturability. Depending on the number of parts you're designing in a year and the level of manufacturing you do in-house, we have a solution for you. Whether it's one-off consulting, if you're doing a part once a year, or our plastic standard, professional, and premium levels with training and mentoring, we've got you covered. After this, a representative from Fisher Unitech will be contacting you, If you have any questions, you can email me directly or ask them of the representative who contacts you. He or she will be sure to get them to me, and I'll be sure to get you an answer.